freedom, and he's very well-known researcher in the area of communications and signal processing. He's also IEEE fellow and has published many papers in the areas of distributed interference management and in general distributed control and signal processing. So I let you the floor, and thanks for attending the course.
Thank you, Pepe. Can you hear me there in the back? Thank you, Pepe, for the kind introduction and for the invitation to this winter school. Actually, it's more winter in Rome than in Barcelona, but anyway, so the title of this contribution is Distributed Interference Management in Femtocell Networks. And essentially, this talk is roughly divided in two parts. In the first part, I'm going to talk about joint optimization of sensing parameters like sensing time, cooperative sensing, detection thresholds, and so on, and radio resource allocation. I will try to show that tackling these two problems, sensing and radio resource allocation, in a joint manner gives you considerable advantages. Then in the second part of this talk, I'm going to talk about radio resource allocation based on a statistical model of the interference. Okay, and then I will draw some conclusions. So first of all, maybe these days you have been exposed to many talks about femtocells, so I'm not going to repeat all the story. But just to mention some key points which are useful for what I'm going to present today. So the potential advantages of femtocell networks are twofold, for the operators and for the mobile subscribers. So in particular for the operators, introducing femtocells, it's a way to increase spectral efficiency. There is some recent work showing that the percentage of increase of efficiency due to the deployment of small cells, femtocells, small cells, and so on, the percentage of increase is much greater than what you will get just enlarging the bandwidth. So you can get really a big advantage in using these small cells or femtocells rather than just enlarging the bandwidth. Then the second point, yeah.
You can get the microphone higher, so
closer
to you.
Is it better now? In the back? Yeah. Okay, then the second point, this is of course well known, you can improve indoor coverage because these are essentially indoor base stations. The other point which is worth to be mentioned is that femtocells allow to offload the wireless traffic into the wired lines. In this way, the operators can free precious wireless resources, bandwidth essentially, to accommodate for further mobile users. So this is clearly an advantage. Now, from the subscriber point of view, of course, nowadays, most of us, we have Wi-Fi at home, or Wi-Fis are well spread in the territory, in the cities, and so on. So we might wonder why is it necessary to have femtocells since most of us, we already have Wi-Fi at home. So there are a few points which are on the advantage for femtocells, and of course I'm trying to highlight the advantages. And some of these are that with the next deployment of LTE femtocells, it is clear that the subscriber can have a quality of service which cannot be guaranteed by the current Wi-Fi development. The other point is that using femtocells, since they are fully compliant with the standard, and you can allow for seamless connectivity of the users, so that for the users essentially will not realize if they are connected to a base station or to the home base stations and so on. So the handoff in particular will be much easier with femtocells rather than with Wi-Fi. So these are some of the advantages of these systems. So in engineering, we are accustomed that every time we get some advantage, somehow we have to pay something. I don't know why there is this sad law, but apparently it's always like this. So which are the drawbacks that we might expect? Well, first of all, since we are going to have a situation with a potentially massive deployment of this femto-access point, it is clear that if we want just to repeat the current paradigm in femtocells, we will have to perform some kind of centralized planning of the radio resource management, but this is going to be very complicated just because of the huge number of femto-access points that you might have. So clearly, global centralized planning is a problem. Then the second point, this is well known, the interference management is a very critical issue in femtocell networks. So of course we have to tackle these two problems. So first of all, we need to study decentralized mechanisms to allocate resources, to avoid the problem, the congestion, the huge signal that we might have if we are going to use a centralized approach. And then we also have to deal with interference management. So in particular, there are several access strategies already foreseen for femtocells. For example, we might have closed loop access. With closed loop, it is clear that we might have more interference just because the femto-access point is serving only its own subscriber, let's say one of two people, the people living in that house, for example. And then all the macro mobile users passing by nearby this apartment, let's say, they might experience interference. So the other possibility is to have open access. So with open access, essentially the femto-access point can allow other people to access to the femto-access point. Just because of this, the femto-access point is able to handle the communication towards also these micro mobile users. In that way, the interference can be eliminated a priori, no? Just because the femto-access point knows that it's serving both the femto user and the macro user. But the problem with this approach is that probably it will be more difficult to be accepted by the subscribers. Why? Because if we are going to buy this femto-access point for our home, most of us we will say, for example, I'm not willing to pay some extra energy bill just to allow for other people to access the network through my own femto-access point at home. So clearly people want to have a closed access. They prefer to have a closed access. Of course, as in many situations, we have to, maybe the best solution would be something in between, like a sort of hybrid access. Okay, this is just to mention the scenario. Okay, within this global scenario, what we are going to talk today is the following. So this is the first part of this talk. So the first topic is this one, is dynamic radio resource allocation based on sensing. Clearly, sensing is a crucial part here, because if we want to allow for a dynamic resource allocation, we want to implement some kind of learning, if you want in general terms, and adaptation to the electromagnetic environment. And of course, we can learn and adapt only if we know the environment, which means that we have to estimate the channel, we have to estimate the interference power across the sub-channels that we might have in an OFDM physical layer structure. So then I will, in particular, I will focus on the joint optimization of sensing parameters, detection thresholds, sensing time, cooperation strategy, all together, and vector power allocation. And then I will talk about the decentralized strategies to implement this kind of allocation. Okay. So again, just to motivate the problem, if we are going to sense the channels because we want to estimate, for example, the interference energy and so on, of course we need time. So if we denote by t sub s the sensing time, this will be part of the first time slot in each frame. So within this time we sense, we estimate essentially the energy of the interference across all the sub-channels. But then, of course, if we dedicate this time for sensing, we are not sending information data at that time, so we are going to experience some rate loss. The second problem is that if we are going to sense the channel only in one position in space, so we have only one sensing node, let's say the femto-access point, for example, of course this can be, unreliable. Why? Just because of fading or shadowing phenomena. So, for example, I'm here, I'm in a shadow, but I don't know. I estimate the energy over a certain subcarrier. I see that the energy is low just because I am in shadow, but of course I cannot know that. Then I decide to allocate my bits over that sub-channel, and I create interference, or I do something that I should not do. Okay? So the way around to overcome this problem is that we need to incorporate some kind of cooperative sensing. So every sensing node should be able to talk with, let's say, few local neighbors so that they can overcome this shadowing effect. Also, they can, of course, exchange their data in order to improve their estimation accuracy, detection reliability, and so on. But also in this case, if I want to cooperate, of course cooperation needs time, needs signaling, and so on. So again, I need to incorporate this extra time, the cooperation time, which I call d sub c, into the problem. So overall, if I take into account both sensing time and cooperation time, if we denote by t the payload duration, we are going to have a rate loss given by this ratio, right? The ratio of the payload time divided by the overall time necessary for sensing and cooperation. Okay. Now, why is it important to address the problem of sensing and resource allocation jointly? Okay, it is necessary to tackle these two problems jointly for the following reasons. For example, when we do sensing, first of all, we want to detect if there are interferences over our sub-channels, the channels we plan to use. And then when we do detection, of course, we have to set thresholds. Okay. Now the question is, what is the best way to find out the optimal thresholds over each channel? Okay. Of course, detection theory is well known. What is in the history of signal processing or decision theory? But the problem is that we should now cast the detection problem within this radio resource allocation within the Femtocell network scenario. So, which are the problems? The problems are the following. For example, if we're going to set these detection thresholds pretty high, so we use high detection thresholds, it will be more likely that we are not going to see if there is someone transmitting there, just because the threshold is very high. And then most of the times we decide for using the channel. So this is why we have in general higher spectral efficiency, which is good. But at the same time, just because the threshold is high, there might be some interferer in some sub-channel which we don't detect just because the detection threshold is too high. So we transmit over that channel, and then of course we generate an interference which we should not generate. Okay, so this is one kind of problem. The other problem, on the other side, if these detection thresholds are too low, what happens is that it will be very likely that we will detect the presence of someone transmitting over a certain sub-channel just because the detection threshold is low. Okay? But we may have detections not only for the interference, but also because of noise. So what happens is that if we just detect noise somewhere, in principle we could use that sub-channel because there is no one there. It was only noise. but we don't use it just because of this false alarm. But then we are missing spectral opportunities. So the rate that we could get is lower than the one that was possible over that channel. At the same time, if these detection thresholds are very low, it is clear that probably we are never going to miss the presence of interferers, and this is why we will have a low probability of generating an undue interference to other transmitters. So you see, in this framework, this explains why, at least in words up to now, this explains why the two problems of detection and resource allocation are very related to each other. Okay. Yes, please. Sure.
With the high threshold, we are losing the spectrum reuse efficiency. And with low thresholds, we are gaining in spectral efficiency.
Right.
But for example, if we go for example, high detection threshold, we will have some reuse efficiency which we cannot use because interference is high. So spectral efficiency will be low. So it means just by looking without any simulation or analysis, having low detection threshold is more favorable. No.
It depends. So this is why I will try to formulate the problem mathematically, putting all these ingredients, if you want, all together. So I will show you in detail, in more mathematical frame. Okay. So I will go to that. And then the last point is that if, besides sensing, local sensing, we also introduce cooperative sensing, of course we need to incorporate local shadowing effects. Just to know, this is the reason why we're going to use cooperative sensing. But again, cooperation requires some exchange of control signals among the players of this game. And then we need to take into account the rate loss that I mentioned before. So again, also in this case, there is some rate loss due to something that comes from the detection and estimation problem. Okay. So what we are going to propose here, as I mentioned before, I will show you at least the way how we formulated this joint optimization problem. And then I will incorporate, in this case, a very simple distributed consensus algorithm just to implement this cooperative mechanism. And then I will show how to handle the interference to primary users in a probabilistic sense. I just mentioned this point to clarify what I mean here. In general, when we talk about the interference problem, the interference that we may generate towards other users, we would like to know the interference power at the receiver. Okay? But of course, there is no link between the, let's say, the macro receiver and the femto transmitter. Right? So there is no way for the femto transmitter to have this feedback from the macro users who are going to tell the femto user which is the power over a certain sub-channel. So how can we establish this constraint on the interference since we don't know anything, essentially, from the macro user receiver? We don't know if a receiver is there, and if there is a receiver, of course, we have no information about the channel. Okay? So the way we tackle this problem, as in many cases, right, in engineering, every time we don't know something, we try to tackle the problem in a statistical sense. So we say, okay, I don't know if there's someone, but I can suppose, for example, that mobile users are uniformly spread across space with a certain density. Okay, I assume that I know the density. This is my only assumption. But everything else is random. I don't know the position, I don't know the channel, but I incorporate a statistical model of the spatial location of mobile users, and I use this model to cast the interference constraint. Okay, so let's go more in detail into the problem. So as in any detection problem, we have essentially a binary hypothesis test. So we have H1 or H0 representing the two possibilities where we have interference or not. H1 means that there is an interferer, H0 means that there is not. We have several of these decisions over all the channels, so K represents a sub-channel in frequency domain. Okay. So what we want to, so first of all we have to specify our utility function, what we want to optimize. So in this case, for example, we want to maximize what we call the aggregate opportunistic throughput. What is this? This is a sort of rate. You see, it's the summation over the rates. Rk is the rate given by the usual channel formula over the kth subchannel with a certain noise and interference power represented by this variance. But this rate here is weighted by a probability. What probability? We use here the probability that we are doing the right thing. What does it mean? It means that we are transmitting over a channel where it is corrected. It is correct to transmit. This means that we are transmitting over the channels which are not busy. They are not occupied by other people. So this is why we weight the rate with this probability. So the probability that there is no one multiplied by the probability that we take the decision there is no one, assuming that there is no one. So this is fine. Pay attention just to a fact. This is not the expected value of the rate, because in principle we could also transmit in another situation where there is someone transmit over the interference over, let's say, the kth subchannel. We don't realize that there is an interference there, and we transmit there. So in that case, I should, add one more term here, implying that there is a probability that someone is there. This is one, but I take the decision that no one is there, conditioned to that event. Okay, but I don't want to incorporate this term into the utility function. Why? Just because I want to maximize this function. So I want to take into account only the positive terms of this rate. I don't want to take into account, let's say, a negative term, the fact that I transmit where I should not. Okay, okay, so this is the rate. And of course, this rate here, this throughput, is weighted by the coefficient that I mentioned before that takes into account the rate loss due to sensing and cooperation. Yes. Yeah. Here I only define the utility function. What we want to maximize is the set of thresholds over all the channels. That will have an impact on this probability here. Yes. And at the same time, we want to so jointly, we want to maximize the power allocation over all the channels, so PK, over all the channels. Okay. Okay. So up to now, the problem is clear, right? We have a bunch of n channels. We want to find out the optimal thresholds over each channel and the optimal power vector such that the opportunistic throughput is maximum. Okay. Yes.
If we are just calculating the throughput in the cases where there is no interferer, then the denominator should not contain interference term.
Yeah, of course. Yeah. In fact, this is why I take this notation, let's say, broadly general, because I incorporate what is there. So I put there noise plus interference, if that is the case, or just noise.
Okay.
I put sigma k squared because the noise could be colored, so the noise power could be varying across sub-channels. I don't want necessarily to have it constant frequency. Okay. Then constraints. So I mentioned the utility function that we want to maximize, but of course we also have constraints. So the first constraint, the most, let's say, the most interesting one, or the most difficult one, is the interference constraint. So what does it mean? That the received power, PR sub k, received by some macro user over a certain sub-channel k, this power, we want the received power to be smaller than a given p minimum, a certain power. In general, we can think of this P min like the noise power at the receiver. So if the interference that I generate towards some interferer is less than the noise power, it's okay, because he's not going to realize that I'm producing interference. So what happens is that we have an interference only if the received power is greater than this minimum value P min. But as I said before, to apply this constraint, I will need to know the channel between the femto and the macro users over each channel. But this is something that is practically impossible to have, no? Just because there is no exchange of information between macro and femto users. Okay, so what we say is the following. We say, okay, there are, let's say, two sources of randomness in the channels between macro and femto users. One is the, let's say, the presence of multipath. We may have several paths from the two nodes. The other is the distance. The distance, of course, is going to affect the coefficient of this multipath propagation. But these are two different phenomena, right? One is distance and the other one is multipath. So what we say is the following. We say, for any given distance, let's suppose that someone will tell me what is the distance between the femto and the macro user. Let's call this distance R. Let's suppose for now that we know it. For that given distance, I may assume, for example, that the multiple paths are statistically uncorrelated. In that case, I can take the conditional expectation of the channel transfer function over the path coefficients. Well, in that case, the expectation over the multipaths in the uncorrelated case will be a constant. The only point to take into account is that this constant will depend on the distance between femto and macro user. Okay, now if we relax the assumption that we know the distance just because we don't know it, we can model the distance as a random variable. So this is like the conditional expectation with respect to the channel conditioned to the knowledge of the distance R. So for any R, we may have a different value of this function here. Well, and eta is the usual path loss exponents. Okay, now what about R? Okay, if we model the distribution of macro users through space as a homogeneous Poisson process with a given spatial density rho expressed in number of nodes per square meter, for example, okay, we may say the following. If this is the distribution of the nodes, what is the PDF, the probability density function of the distance between the femto access point and the nearest macro user? Okay, this is something that is known. Actually, it's a very simple formula. The PDF of the nearest femto access point, in this case, of the nearest macro user, will be a Rayleigh PDF. So we know the PDF, and that PDF will only depend on the density. So this is why the only information we need is an information about the density of this node. Okay, if we know this density, we may say, okay, the power, the average interference generated by a femto access point towards macro users can be expressed in this way. You know, just inserted the formula for the expected channel transfer function conditioned to R, and then we express the constraint in a probabilistic term. So what we say here is that we want that the probability that the received power will be less than the threshold at the receiver. We want this probability to be very high so that we are confident that we are not going to generate an interference. But we express this confidence through a probability. So if we set this probability pretty high, let's say 90%, we might say that with 90% of probability, the interference that I generate towards my nearest macro user will be very low for him, or her, for the macro user. Okay? So at this point, you see, this is the probability of an event that depends only on one single random variable, which is the distance. but this distance is a Rayleigh random variable, so this probability can be computed in a very simple way. It's a simple integral. So we compute the integral, and then this constraint becomes this one, which is very simple. We have just a summation of transmit powers over all the subchannels, weighted by some coefficients, and these coefficients depend on the probability P0, on the beta, which was on the expected value of the transfer function, on the density of the macro users, and on the minimum detectable power. Okay, so this is a way to handle our lack of knowledge about the channel between femto and macro users. Okay, now the usual detection problem. So here I'm going to use the simplest form of detection, which is the well-known energy detector. So what we say is that over each channel we have two hypotheses, either noise alone or noise plus interference. We estimate the energy over each channel. This might be a weighted energy if we have some priori knowledge about the noise variance and the interference variance, but if we don't, we just take the energy. Okay, then of course we know very well that this estimation will be, of course, better and better the greater is the number of samples that we use for the estimation. But of course, if we are going to use too many samples, we are going to pay too much in terms of rate loss. Okay? So what we might do is that, for example, let's suppose I take 10 samples. The node nearby myself will take other 10 samples and so on. I estimate my local energy. He estimates his local energy. We exchange these two energy. In one step, it's like I have 20 samples. So, of course, I gained a lot, no, with just 2. Right? If I repeat, with other 9 people, I can get 100 samples very quickly without waiting for 100 samples for the estimation. So the trick is very simple, right? Everyone will estimate this energy here, and then we exchange this parameter, and this will be a very simple way to have, for example, an average across the cooperating nodes. Then at that point, our estimator will be a double summation over the number of samples in each node and a summation over the number of cooperative nodes. Okay? And then, of course, we will take this energy and we will compare it with the threshold to take our local decision. Okay. Well, in general, here the problem, if we analyze it very, correctly, it's not very easy, even though it's going to boil down into chi-square statistics and so on. But if the number of samples is sufficiently large, we can invoke, as in many other cases, the central limit theorem. So in this case, we can express the detection probabilities and the false alarm probability in closed form, even though approximate. So the relationship would be like this. Now, I mentioned this, even though this is well known, of course, because what is important to take into account here is that there is a one-to-one relationship between the false alarm rate and the probability of detection and the detection thresholds, of course. So we can play with these parameters. So not necessarily we need to play with the probability, or we might also choose, for example, detection threshold and PFA and derive the other one. So they are related to each other, just because they depend on the same coefficients, essentially. Yes?
So you have samples from different nodes, right, which you are aggregating. Yeah. And those might not be IID now. They are, of course, independent, but they might not be identically distributed. So how do you think
in this case, I am assuming, I didn't say that. Thank you for the comment. In this very simple framework, I am assuming that the measurements at different nodes, they are statistically independent. This is why I end up into this easy form of the. Otherwise, I should take into account the correlation among the nodes.
No, actually, independence assumption, I would say that okay, it will hold to some extent if the nodes are kind of spatially apart, but it's the identically distributed assumption which kind of bugs me, especially if you are applying central limit theorem.
Well,
you need.
Well, you could weight those energy in the right way. This would be the optimal detector.
Okay.
I mean, under the Gaussian assumption, so you might either have Gaussian noise or a useful signal which we might model as a Gaussian noise, which of course it is not. Okay, but within this assumption, the optimal detector would be something like this.
So you are weighing the samples in a particular way so that you get a Gaussian at the end.
No. The Gaussianity comes from, let's say, from the central limit theorem.
No, but for the central limit theorem, you need all your samples to be identically distributed.
No, that's not necessary.
No?
That's not. That's the way that we usually
okay.
study it, in the first, let's say, class on signals and systems or whatever. But the central limit theorem is valid in a much more general context. Also, you can also incorporate some kind of correlation among the random variables.
All right.
They should not be, of course, correlated one-to-one. This is clear. This is just intuitively speaking. But if they are not correlated one-to-one, so essentially you have different variables. Also, if there is some correlation among the variables, you might still invoke the central limit theory in a more general form, of course.
Okay,
it's not the
thanks.
usual one. Sure. Okay, so this. Okay, so now I just mentioned the fact that local nodes might decide to exchange those local energy estimates to improve their own estimation. But of course, this exchange of data needs time to converge. Okay? So the other problem we have to take into account here is that we want to achieve some kind of trade-off between the improvement that we can get through cooperation and the loss that we have to pay because of establishing this cooperation. Okay. Now, if we implement this kind of cooperation through a consensus meaning that I just exchange parameters with local neighbors, they send me their parameter, I send them my own estimates, we take local averages and so on, everyone does the same. At the end, it's very easy to show that under very mild conditions, everyone will converge to the average of the values that we exchange. Now the point is, how do we quantify the convergence time? Okay? Now, even though I'm not going to the detail about this, but you may think intuitively that what happens is the following. The convergence time depends on the connectivity of the nodes exchanging data. I'll try to clarify myself. If, for example, let's suppose we have this network of people who wants to cooperate, and let's suppose that I am connected with everyone. I have a direct link with every one of you, right? So at that point, I can exchange my data with every one of you. So after one slot, or the slots necessary for you to send me this data, I'm done. Because I have all the data, I just take the average, very simple, it's done. But of course, to do this, I have to pay a lot in terms of power, because I need to establish direct links with everyone, so probably also with distant nodes. On the other hand, the contrary, on the opposite side, I might be connected only with my neighbors, with my nearest neighbor, okay? He will be connected with the next, and so on. So if this is the connectivity, so the connectivity is very low in this second situation, of course it will take more time to converge, because I exchange data here, he will do the same, she will do the same, and so on. So this will take more time. But at the same time, the power might be much less, just because every one of us is transmitting at a very low power to exchange this data, just because I'm communicating only with my nearest neighbor. Okay? So the problem is, how do we quantify? It is clear that the convergence time depends on the connectivity, but we don't know the connectivity. I'm just talking with my nearest neighbors, and I don't know how many are connected, how many are there. I transmit with a certain power. Everyone within my coverage radius will send me back information, but I don't know how many of them I will have. So how do we tackle this problem? Again, the same trick. We just assume that all these nodes, the cooperative nodes, are distributed randomly in space with a certain density, not necessarily the same as the other distribution, a certain density. So given this density, we might think that there is a link between two cooperative nodes only if they are within the coverage radius of each other. So this is the model, very simple. And this is what is known in random graph theory as the random geometric graph model. Okay, so what is a random geometric graph? It's a topology which is essentially captured by the so-called adjacency matrix A. So this is a matrix, it's a binary matrix, which might be whose coefficients are only 0 or 1. So the coefficient Aij is equal to 1 if the two nodes are within the coverage radius of each other, or in the other case, the coefficient is equal to 0. So very simple matrix, but it's a random matrix, just because the position of these nodes, the y, I, and j, which are there, these positions are random variables. We don't know them, okay? So the randomness is there, okay? So A, the adjacency matrix, is a random matrix. Then it is useful to introduce two other matrices for describing the properties of this communication. One is the degree matrix. This is a diagonal matrix whose diagonal entries are just the sum over the Aij over the second subscript j. Okay, so just the summation over those coefficients. And then the other important matrix is the Laplacian L. L is simply the degree matrix minus the adjacency matrix. Now, once you have these two matrices together, it is possible to show that the convergence time, what is interesting for us, the convergence time depends primarily on one single parameter. This single parameter is the second smallest eigenvalue of the Laplacian. Okay, so it's this magic number is the, what I say, this is also called algebraic connectivity. So the algebraic connectivity in mathematical terms is the second smallest eigenvalue of the Laplacian. Okay. But now the Laplacian is random, okay, because it's made of random coefficients. So we are talking about the second smallest eigenvalue of a random matrix. Okay, so it's not very trivial. Nevertheless, we recently found out an asymptotic expression for this eigenvalue. So we show that the eigenvalues of the Laplacian matrix describing a random geometric graph, okay, these eigenvalues are going to be more and more confined around a certain point, so they tend to become like deterministic variables as the number of nodes in the network goes to infinity, so asymptotically. So what we proved is that asymptotically you can approximate, of course, because we are not going really to infinity, so for any number of nodes and for a given coverage radius R, you can approximate the value of the algebraic connectivity in this way. So this is, it's a simple formula. Of course, it is an approximation, but it's good because now we can play with this formula rather than just running, computer simulations and so on. So what we may say is that once we have this lambda 2, the convergence time of this simple cooperative scheme is essentially inversely proportional to the algebraic connectivity. So we have a simple way to tackle the convergence time of this cooperative mechanism. Okay, now we are close to the formulation. We are trying to put all the ingredients of this complicated cake. So I put cooperation. Now I need to talk about the mechanism to find out the thresholds. Okay, to find thresholds, we need to specify the detection criterion, which criterion we are going to use. Well, for this case, we thought that it would be reasonable to assume the well-known Niemann-Pearson criterion. So Niemann-Pearson says that you want to find out the threshold so that for a given false alarm rate, you want to maximize the detection probability. So you have a constraint on the false alarm probability. You don't want to exceed a certain false alarm probability, and under that constraint, you want to maximize the detection probability. Okay. Then, if we have this constraint on the false alarm rate, we might say, okay, then it is not useful to have different false alarm rates over different subchannels. So we assume that the false alarm rate is the same over all the frequency subchannels. But of course, this doesn't mean that the thresholds will be the same, because the noise power or the interference can be different over different subchannels. So the thresholds are going to be different. What is constant is only the false alarm rate, which comes from the Niemann-Pearson constraint. Okay? So we say, do you remember that? So this is the opportunistic throughput that I mentioned at the beginning. So it's the summation of the rates weighted by the probabilities. So here there was also the probability of not making mistakes, which was essentially 1 minus the false alarm probability. Right? So now, just because that term is constant, it doesn't depend on k, I just took it out of the summation here. And this is the usual rate loss term. The only difference is that now I incorporated the estimation on the convergence time. Okay? So now everything is here, right? Because we want to maximize this function that depends on the transmit power, on a coefficients that incorporate channel, noise variance, interference variance, and so on. Everything is on this coefficient. Then this is the a priori probability that nobody is transmitting there. And this is 1 minus false alarm rate. What is 1 minus FFA? Means that nobody is transmitting on the kth channel, and I decided that nobody is transmitting there. So I took the correct decision over that channel. Okay. So this is the function we want to maximize. Which are the constraints? The first constraint is the interference constraint that I mentioned before. So this is going to be the interference constraint. So you remember we had a summation over the transmit power by a certain coefficient that depends on our detection criterion. And this is why we have 1 minus detection probability here. What does it mean, 1 minus the detection probability? Is the probability that somebody is there, somebody is transmitting, but we miss. We don't detect this interference and we transmit. So we do something which is wrong. What is the probability of making this wrong action? Is the probability that, as I said before, someone is transmitting and I decided that nobody is there. So the probability of this event is 1 minus the detection probability. Okay? So this is why we weight the transmission power pk by this probability times the probability that really someone was transmitting over the kth subchannel. So this is the interference constraint that I mentioned before. Now, which are the optimization variables? We are optimizing over the power allocation. Okay? We also want to optimize over the thresholds, as I mentioned before. But now, the interesting part is that actually we only have this unknown, the false alarm probability, because the detection thresholds will be given a certain false alarm probability, we will derive the detection thresholds. This is why we don't need now to compute directly the detection thresholds. We just want to compute the optimum false alarm probability, and then we will derive the thresholds consequently. Okay, so I said this is the interference constraint, and this is the relationship between the detection probability and the false alarm rate, and this is an expression, it's a direct link between the PD that we write here and the false alarm rate, which is here. So again, these are coupled, the constraint and the utility functions are coupled to each other. Okay. So finally I can state the problem I want to solve. We want to maximize the expression up there with respect to the false alarm rate, with respect to the power allocation vector P, and with respect to Ks. Ks is the number of samples that we use for our energy estimation. Okay? So we optimize over sensing parameters, incorporating the sensing time, Ts, the cooperative time, Tc. We optimize over the false alarm rate and over the power allocation, Pk, under the interference constraint. And then, as usual, we have to incorporate also the common transmit power constraint. We want that the transmit power should be less than a given power budget, as usual. Of course, the power coefficients should be greater than 0, or at minimum 0. And then we also want that the false alarm rate should be a positive or non-negative, because it's a probability. And of course, it doesn't make much sense to have a PFA greater than 1/2, because that would be too high. So these are the constraints that we put into the problem. Okay. Now we go to our convex optimization books. We look at this problem. So when we analyze this problem in the joint domain of the power vector P, the false alarm probability, and the number of samples Ks, this problem is not convex. But, there is a but, this is important. What happens is that if someone will tell us the false alarm probability and the number of samples Ks, this problem is convex. Okay? If I will know, someone will tell me, no? Ks and false alarm probability, the problem is convex. So I do the following. I assume to know the false alarm probability and Ks, and I find the optimal solution. And the solution is like this. You see, I think that this expression looks nice to me. Why? Because it is the usual water filling solution that we might encounter in all problems like this. The only interesting difference is that now the water level is not exactly water level, because it's a multi-level water filling. This level is going to vary across sub-channels. This level is going to depend now not only on the channel coefficients, on the power as usual, but it is also going to depend on the false alarm probability and on the number of samples used for the estimation. This is why this water level depends on those parameters there. Okay? But of course, I have not solved the problem yet. Why? Because I said, let's assume that I know the false alarm probability and the number of samples. But I don't. I don't know, of course. But I can do the following. Just because I have this closed form expression for the optimal power vector, I can plug this expression back to this utility function here. So I say, in any case, I know that there is a one-to-one relationship between false alarm rate, number of samples, and power vector. So I substitute into the power vector P the formula, the water filling formula that I mentioned before. Okay? This is useful. Why? Because when we do this, of course, we end up into a utility function where we substitute the optimal power vector function of the false alarm rate and number of samples. But now we only have a function of 2 variables. So still, the problem was not convex, but at least it's simpler than before, because instead of having n plus 2, where n is the number of subcarriers, instead of having n plus 2 unknowns, I only have 2 unknowns. Okay, now, of course, the critical point is to study the behavior of this function here with respect to these variables, because if this function will be, will go up and down or vary a lot, having multiple maximum, of course, we will still be in trouble. But fortunately, just a second, this is an example, but also if you change the parameters, you are always going to end up into something that looks like this. So this is the utility function as a function of the number of parameters, Ks, and the false alarm rate, PFA here. So you see what happens is that there are 2 very nice features. One is that this function is clearly a smooth function, and the most important thing, it is a smooth function of these parameters. It is not convex, but who cares, right? What is important is that we only have one maximum for this function. Yes?
Could you return to the page before? Yeah. In this expression, even omega k is not known. It will depend on the constraints.
Yes. The WK, you mean the
yes,
the water level?
Yeah.
Yeah, yeah. So what we do is the following. To find out this expression, we impose the KKT, the Karush-Kuhn-Tucker conditions. So at that point, you express the optimal power vector in this way, but somehow hidden in this expression, there are all the Lagrange multipliers there. Okay. So what we do is the following. We say, okay, the expression is like this. And remember that there are Lagrange multipliers, and we know that the way to find out those Lagrange multipliers is to impose the constraints. Right? So the constraints will be like this. Right? We will have the transmit power, and of course we are going to transmit at the maximum power, and we want to be essentially at the equality there. Okay? Then we impose the constraints to find out the Lagrange multipliers, but of course this step is a numerical step. So the important point here is that, so in principle we substitute this expression there, but this expression, at least up to this point, still depends on the Lagrange multipliers. So then we substitute and we solve numerically the problem. But there's no loss of optimality. This is the key point, I think, in doing this. Just because the relationship between false alarm rate and number of samples on one side and the power vector allocation is one-to-one. There's one relationship, which is this one. I don't know if I'm clear. Am I clear? Did I answer to your question?
Yeah. Yeah. Thank you.
Okay, so what we may say here, even though we cannot formulate it as a theorem, okay, probably there is a way, but at least we haven't been able to formulate it as a theorem to say that there is only a unique pair of points, false alarm probability and number of samples, such that this function is maximum. And if you want, one of the complicated aspects of this analysis, just to find out, you know, just to prove that there is only one maximum, one of the complicated aspects is just the question that was raised before, that the coefficients that we substitute, in effect, they still depend on the Lagrange multipliers, which we can only find numerically. So it's like we have a function, but it's a function that is not easy to analyze, because it's not expressed in every single unknown, because there are unknowns that I can only find numerically. This is why it's difficult. I cannot take derivations, for example, because I will not know the Lagrange multipliers at a certain stage. Okay, but still, looking at the numerical results, the problem clearly admits only one solution. Actually, if you leave on aside mathematics for a while, and if you think intuitively to this, I think it makes perfect sense that there is at least only one maximum, at least in each direction. Why? Because what happens here is that, for example, let's assume there is a fixed false alarm probability. For any false alarm probability, if I am going to change the number of samples, at the beginning I'm going to improve. Why? Because my estimation of the energy is going to be better and better. This is why I improve. Okay? But at a certain point, I have a decrease. Why? Because if I take too many samples, the extra improvement that I get is marginal, is small, but at the same time I'm going to pay a lot in terms of rate loss, just because most of the data that I'm using is for sensing instead of sending information data. This is why at a certain point I have to lose. This is why I only expect one maximum in this direction. Okay, the same happens in the other direction, along the false alarm probability, if you think about it. So, in a sense, I think this is intuitively explainable. Mathematically, it's more difficult to handle. Okay, this is another curve that shows the opportunistic throughput as a function of the false alarm probability. For different values of the P0, P0, remember, was the probability, that we are confident that we are not generating too much interference to the macro users. Okay, so we want to use high values of the P0 just to be sure that we are not harmful to anyone. Okay, and so you see, for any value of P0, there is only a unique value of the false alarm probability that maximizes the throughput, and this is what we see there. Okay, let me move more quickly. Okay, here I plot the opportunistic throughput as a function of two parameters, essentially the path loss exponent and the density. So these three curves are for three values of the density of the macro user's deployment. So this is for 0.1, I think was 0.1 nodes per square meters. This is 0.2, 0.3, and so on. So you see what happens is that as you increase the density of macro users, the opportunistic throughput is going to decrease, which makes, of course, sense. The nice point is that you are able to quantify this improvement.
Going back to the previous slide.
This one?
Yes. With the path loss exponent increasing, its throughput is decreasing.
Say that again?
With the path loss exponent increasing, the throughput is decreasing as well.
Yeah, also, exactly. Yeah.
Shouldn't it be other way around, because you will have less interference? If the path loss exponent is high,
yeah, but you also have you're also computing the throughput, so also in your own channel you are going to experience more attenuation.
Mm-hmm. Because generally the path loss exponent is more favorable to interference. It depends how the path loss has been modeled, but
because
in
this
macrocellular
is present in both, in the direct path and in the interference path. So this shows that, well, this is true in general, right? Yeah, I understand your point. What your point is that since I'm concerned with the interference that I'm generating, of course, if the channel attenuates more, I produce less interference. This is true, but at the same time, take into account that the path loss plays a role also on the direct path. So the combination, at least for these values, will give this result here. But I agree, in general, it has to be studied. I mean, taking into account both.
If it's same for both, then it should not affect. It should not affect, depend on path loss. The reason I think it's decreasing with path loss is because we are not taking into account
I don't remember
interference.
if here we assume the same path loss for the femto to macro or for the femto transmitter to the femto receiver. Now I don't remember if we use the same.
But
I don't.
But I think it's since it's opportunistic throughput and we are not taking into account the interference. So as the path loss is increasing, exponent is increasing, so the throughput is decreasing, because the interference is not affecting anyway. If the exponents are same, then it should means if the interference exponent, path loss exponent, and the signal path loss exponent is same, which is not same in macrocellular. It's same, it's
so
flat.
But it's not so. I understand the point. It makes sense. It makes perfect sense. I'm just thinking. But what I think is that once we write those constraints, the interference constraint, and we impose the probability
that there is no interferer.
I guess that just because we cast the problem in that way, probably we are going to increase the transmit power, because the constraint takes into account that, for example, now there is a higher attenuation, and then what should be checked if this increase in transmit power affects the power that you should use for your own good transmission to the femto receiver. This is why it is not so one-to-one. It is complicated just because they play different roles in the utility function and in the constraint.
Okay, thank you.
Okay, And finally, for this part, here I'm plotting the gain, the relative gain in throughput that you can achieve through cooperation. So this is like the increase, the rate increase due to cooperation. So it's the rate including cooperation minus the rate without cooperation, so the non-cooperative case, divided by the rate in the non-cooperative case. And this is this function g is plotted as a function of the p0 probability, the probability that we don't want to produce any undue interference. So you see, this is a factor that with all these values here is always greater than 1. And in particular, the interesting part of this curve is here, so around, let's say, 0.9, and we can see that there is a considerable gain just out of local cooperation. Of course, here I have to be more specific because, for example, I assumed a certain number of nodes, but here there is an extra problem which is not taken into account here. It should be. The problem is the following, that from a certain point of view, I would like to have the greatest number of cooperative nodes so that in principle I could improve, keep improving my performance. But this is true only if we are going to estimate homogeneous things. But if we are too far away, probably it is natural that you are going to experience something that is totally different from what I experience, even irrespective of fading, shadowing, and so on. This is why up to beyond a certain point, I should not take these averages, because I will be averaging things which are not, which should not be averaged. Of course, I didn't take into account this aspect here, but in a future development, this should be taken into account. Some kind of homogeneity of the electromagnetic environment we might expect. Okay, so. Well, the conclusion for this first part is that for our point of view, of course, the joint optimization makes sense, and it can be handled with, let's say, not incredible complication, extra effort, because some of the parameters can be expressed in closed form, others not, but it's, numerically speaking, it's not a very difficult problem. And yeah, as a further development of this area, we should include more advanced forms of cooperation rather than just consensus, as I mentioned before. We should consider non-homogeneous interference, and we should also take into account more explicitly the power necessary to establish the link for cooperation should be also taken into account. So in a way, one should take into account a global power, considering the power for cooperation and the power for transmission. Under this global parameter, one should probably get the optimal values. Okay, now I move to the second part. I have 20 minutes. Yes. Okay, I'll try to speed up. So what we do here is that we want to, again, do dynamic power allocation. The difference here is that we estimate the interference over each channel, and we say, okay, if instead of just estimating the energy, we also estimate the transition probabilities of the active state of the interference over each subchannel, we may do something more complicated than what we did before. So it's like we incorporate an interference statistical model in this problem. And for example, at least here, we model the interference over different subchannels. We model the activity, the interference activity, as a set of discrete time Markov chains over different subchannels with their own transition probabilities, possibly different over different channels. Then we follow a Bayesian approach. And so what we want to do here is that we want to estimate the power at the beginning of a frame, and then we allocate power not only on that slot, but over a certain number of consecutive time slots, and of course several frequency slots, just taking into account the estimation on the first slot and the estimation of the transition probabilities. Okay, the scenario that we will consider will be essentially of two forms. In the first part, just for simplicity, we will consider a single femto-access point, okay? And then in the second part, we will consider multiple femto-access points. Here there is a basic difference into these two scenarios, and the difference is the following. If I am, in a sense, cognitive in a broad sense, just meaning that I am learning from the environment and behaving consequently, of course I react dynamically to what happens to the channel. So if I am the only, let's say, femto user or cognitive user, then I am the only one reacting, but if all the other users are macro users, they are not counter-reacting to my own choices. Okay, so this is one scenario. The other scenario occurs when we have multiple femto-access points. Why? Because in that case, one femto-access point will learn and adapt consequently, but then also the other femto-access points will react to this decision, and so on. So this will create a dynamic mechanism, and you want to find out if this, let's say, population of femto-access points will converge to an equilibrium. Okay, so this is why we formulate this problem as a game problem, where the players are the femto-access points, and we want to find out the conditions under which there exists an equilibrium, and to check if the equilibrium is efficient, and if there are ways to improve the efficiency of this game. Okay, we will also consider two classes of problems. One where we maximize the rate under a power constraint, and the other where we impose a rate constraint and we want to minimize the power. The difference with respect to what is known in the literature is that now we don't know the interference power, and we model this power as a Markov, as a set of Markov chains. So our power allocation will depend on the transition probabilities that we estimate through time. Okay. So over each channel, we consider this binary random variable as Km. So K is the frequency index, M is the time index. Now we have this further coefficient, which is time. So this will be either 0 or 1, 0 if the subchannel is idle, 1 if the subchannel is busy. And then the probability for a channel to be either idle or busy will evolve in time according to the well-known Markov chain. Okay. And this will be the transition probabilities, right? Okay, so this is well-known, basic Markov chain. Now, of course, in principle, we don't know the transition probability. In practice, we don't know them. We can estimate them. Well, the maximum likelihood estimator of the transition probabilities is very simple in this case, because it's essentially a count of number of transitions. So if you take this ratio here, you can estimate this will be the maximum likelihood estimation of the transition probability from the state I to state j, from one time index to the next. And these are the number of times in which the activity switches from one state to the next. Okay, this is well known. Now, let's go directly to our problem. So we want to maximize now the expected rate. So this is the expected rate, expected with respect to what? With respect to the interference activity. So just because now the interference activity is not deterministic, we don't know if there is an interference. We only know that the interference is present or not with a certain probability. So the average, the expected rate will be the average of the rate with the probability. For example, let's suppose this term here, A and K is the channel over noise. So in this case, we only have noise. So we are going to have this rate only if that channel is idle. So there is no interference on that channel. This is why we have to multiply this rate by the probability bkm, beta km, that at time m over sub-channel k, the channel is idle. Okay? Okay, plus the rate that we have over channel K and slot M in the situation where besides noise we also have interference. So this is the case where we have interference, and this is why we have to weight this rate through with the probability that indeed there is an interference there. Now the interesting part is that these coefficients are going to evolve in time according to the Markov chain model that I described before. Okay? So again, what we want to do is we want to find out the optimal power allocation coefficients, PKM, across frequency and time, depending on the transition probabilities and on the channels that we have. Okay. Okay. So the problem is we want to maximize the expected value of the rate averaged over the interference activities, subject to the usual power constraint, the summation of the powers less than a certain value, and of course the power should be non-negative values. And we also impose some mask constraint, meaning that the power should not overcome a maximum threshold P max. Okay, when we formulate this problem, again, this is very simple. If you this problem is convex, there's no problem here. So you can solve it, and if you apply the KKT conditions, the optimal power vector looks like this. Okay, so again, you can find a closed form expression for the optimal power allocation. Now, the interesting part is that the coefficients appearing here, they depend now not only on the channel, but they depend also on the transition probability of the Markov chains describing the interference activity. This is the interesting part. Now, if you want to, we also checked through a different path the correctness of this expression, if you want, because we took the limit of this expression just making the transition probabilities go into 1 or 0 in a coherent form, and we check that this form will go to the water filling, which is the right solution, as we know. Okay, so this is a sort of generalized water filling. Okay, so in that case, we consider the rate maximization under a power constraint, but in femtocells, it might be even more interesting, if you want the opposite problem, the one where you impose a rate constraint, a minimum rate, and you want to find out the minimum power necessary to guarantee a minimum rate. So we say we want to minimize the sum of the powers subject to the constraint that the expected rate, this is the novelty, the expected rate should be greater than a certain value R0. Okay. Now, the important point here is the following. This makes a sort of difference with respect to the previous case, even though they look like very similar, but they are different. Why? Because in this case, we need to check a sort of feasibility condition. Why? Because if we, for example, we put a value R0 too large, there could be cases in which there is no power vector P that guarantees that our expected rate will be greater than the value R0 that we imposed a priori. So we need to check a priori this kind of feasibility condition. If the feasibility condition is ensured, the optimal power allocation looks like this. So essentially, it's the same form as before, of course with different parameters, but the same kind of expression, where again the coefficients appearing in this sort of generalized water filling now depend on the transition probabilities. Okay. Now, the more interesting scenario occurs when we have now multiple FAPs, multiple access points, because everyone will react to the decision of the other femto-access points. So this is why we formulate this problem as a game where each player, Q, wants to maximize its own expected rate, this kind of Bayesian game, subject to the power constraint, okay, and where this constraint can be expressed in this form, implying, as before, that the sum of the power is less than a certain value, non-negative powers, and so on. Okay, so if we look at this problem, we can check, and this is very easy, that the payoff function of each player is a concave function, and the feasible set of every player is a compact and convex set. So under this condition, the game admits a non-empty solution. So there exists a solution. This is the first easy thing to check. Then in a previous paper, we showed how to solve this game, find the equilibrium, through a variational inequality approach, which allowed us to propose this kind of iterative gradient projection algorithm. I will not go into the details of this. This is already in the literature. Now, because I want to concentrate with other things. Now, the important point here is that the equilibrium that we are going to find, this equilibrium might not be efficient at all. Now, this might happen. Even if all the nodes converge to a certain equilibrium, this equilibrium can be far from the so-called Pareto boundary frontier. So what can we do to improve upon the efficiency of this game? Okay, the usual way is that we need to incorporate some coordination. Again, we need to make nodes to coordinate with each other. When we say coordinate, now we distinguish between coordination and cooperation. When we say coordination, we mean that these nodes are only exchanging some parameters. They are not exchanging data. They are only exchanging parameters. Okay. So what happens is the following: is that if you want to make your equilibrium to be more and more efficient, you should take into account, when you choose your own strategy, let's say the damage that you do to the other people. I'll try to put it differently. Every time I transmit over a certain channel, of course I'm also generating interference to the others. So if I take into account the extra interference that I produce to the other users when I do my own maximization, probably I will do something better than in the purely competitive case. Actually, this can be proved. Okay, there are these beautiful papers on pricing mechanisms. There was this paper by Shi, Berry, Honig, and so on, proving that if instead of maximizing your own rate, you maximize the sum of the rates of all the users, you may approximate the solution. This would be an approximation, just because if you consider the sum of the rate, this is a non-convex function of the power allocation, so it's a very difficult problem to solve. Nevertheless, you can approach this solution through the pricing mechanism. Okay? What happens, of course I will not go into the mathematical details, it's like you do the same. When you take the sum of the rates, your own rate is a convex function, I mean it's a concave function of your power allocation, and you want to maximize this function, so this is fine, right? Because it's a concave function of powers, so this is fine. But your power also appears in the rate of the others, and when it appears there, it's a convex function. For the other rates are convex function of my own power. This is why we have a summation of function where my own rate is a concave function of my power, plus other terms which are convex functions of my power. The trick, if I have to say, without the mathematics, the trick is that I consider the good rate, my own rate, as it is. So I don't make any approximation. So I keep this concave function because that is fine. But for the convex part, I approximate that convex function as a linear. So I make it's like taking the, let's say, first order Taylor series expansion. This is why it's an approximation. And of course that expansion depends on the point where I do the expansion. This is why I need an iterative mechanism. So I'll try to explain what happens, without mathematics. I don't know if I'm clear, but I'm just trying to give you the intuition underlying that. Okay, so in essence, you need to exchange these prices, and these prices are, you see, minus the derivative of the expected rate with respect to the interference that you generate towards the others. So when you incorporate these terms into our formulation, we say that we have this game where we want to maximize the expected rate, okay? But now we also have an extra terms that takes into account the interference that we generate towards the others. Okay? In principle, it looks like I just have a loss, right? Because instead of being, in the competitive case, I am purely selfish. I only consider myself, right? So in principle, one could think, erroneously, but one could think that this is the best for myself. Forget about the others. Why? I want to be selfish, and I just do the best for myself. So one could think that actually that should be the optimal strategy. This is not true. Why? Because this is a game. So every time I adopt a strategy, also the other players are going to adopt a strategy. So what happens here, again, intuitively, is that if I'm not selfish and I consider what is the interference that I generate to the others because of my actions, I know that also the other players are going to adopt the same strategy, so they will also care about the interference they will produce towards me. This is why at the end, indeed, I can reach a better result than in the purely competitive case. Okay, so again, we solve this problem. This can be solved in closed form, and this would be the optimal power allocation in a form close to the previous one. Okay, this is the algorithm. I only have 3 minutes, so I will show you just the result. Okay, this is the equivalent case where we minimize the transmit power under a rate constraint for all the players. So, okay. And well, in this case, this problem can be formulated as a potential game. Potential game means that there exists a function called the potential, such that any strategy that increases the payoff, the local payoff of a player, is also going to increase the potential function. And this is true for every user. So it's like every time, even though we are doing the best for ourselves, if the game is a potential game, even without knowing, we are doing the good for everyone. This is the goodness of potential games. But it's a generalized potential game because there is a constraint in the feasibility set. So the feasibility set of each player is dependent on the actions taken by the other players. Okay, I will not go into this. It's complicated. Let's go to some simulation. So first result here, I plot the expected rate as a function of number of time slots where we allocate power for different conditions. The conditions are the following. The green one, the top one, is the case where we know in advance the activity of the interference. Like we know the future. Someone tells us the future over this number of time slots. Okay? This is an idealistic case, but just as a benchmark, right? So the green curve is the one where we know the future. All the other curves are only assuming a statistical knowledge. So we estimate the transition probabilities. We use them in the algorithm that I proposed before. So you see what happened. And then, of course, we may use models with different order for the discrete time Markov chain. So as the order increases, you see we go from 1 to 2 to 3. So the blue will be the order 3. We see that we start from here. So this is the case where we have no knowledge about the future. It's like we measure something here, and we assume that the future will be exactly the same as the present. This is what gives this curve here. Okay? The simplest case, I estimate something on this time slot, and I assume that on the next time slot, the situation is going to remain exactly the same. Okay? In the other case, we are incorporating the estimation of the transition probability, and we find out the optimal power allocation in that case. So you see, what happens is that you can approach the ideal case of perfect knowledge as the order of the Markov chain increases. See, you go there. And you can also check what is the penalty that you have to pay because of the lack of knowledge of these transition probabilities. Because, for example, the blue curve with the squares on top is with transition probabilities known. The other ones are the case where you estimate sequentially these transition probabilities. So there is an extra penalty due to the estimation errors. Okay. This is what happens to the sum of the rate as a function of the number of time slots, because you start estimating something, so at the beginning your estimation would be very poor. Then you sequentially update. So after, let's say, 30, 40 blocks, this shows that essentially you reach the final values. Okay, so you don't need an extremely high number of blocks to converge. Okay, now the converse. We are running now the minimum power problem under a rate constraint. So again, the green curve is the power that you need to guarantee a certain rate in the case where you have perfect knowledge of the future. So this is the green case. The blue one is the case where you assume that the future is going to be the same as the present. So you have, and this is the loss that you pay. And these are the cases that we achieve with our algorithms where we estimate the transition probabilities. Okay, now this will be the last two slides. So I don't want to make you stand more than necessary. So the question now is to be competitive or to be cooperative, right? So what I compare here is the sum rate that we achieve in the purely competitive case and the sum rate that we achieve in the cooperative case here. Okay? Again, in the situation where you have perfect channel knowledge, no channel knowledge, just assume that the future is equal to the present, and with our Bayesian approach, the red curve. So without cooperation, with cooperation. So if you check the numbers that you get into this case, you may see that there is a considerable advantage in terms of sum rate, looking at the numbers here, even if the behaviors are similar, but the numbers are greater in the cooperative case. Meaning that if you can afford for this cooperation, so this exchange of prices, you are just exchanging prices among the nodes, you may get a considerable advantage in terms of rates.
Why is so little difference between the competitive and cooperative?
So little, I don't know, it depends. You know,
because
this depends, of course, on the channels, conditions, and so on.
In non-cooperative
these are not
games,
absolute numbers, right? They are conditioned to the channels that we generated in that case, and on the transition probabilities, of course. I think in this case, local cooperation, yeah, but through a sort of network. So it is like as if you are cooperating with all the ones. So here, for example, we had 10 femto-access points allocating over 12 consecutive frequency subchannels and different numbers of time slots. Okay, so but these 10 are all cooperating with each other. So it's like this is the sum rate for all of them.
So the sum rate is excluding the signaling required for cooperation?
Yeah. Here the sum rate is the sum rate, so it doesn't take into account the
signaling.
cooperation loss.
Yeah. Okay, so effectively the game would be lesser than this.
Actually, it would be less, at least in this case, yes. That's true. Okay, next point, the other game, the mean power game, again, purely competitive or cooperative case, and you may see a similar result as before. Of course, here this is the best case, the ideal one. There's also something that I didn't mention before. You see, look at this curve here, for example, right? So this is the idea. This is our solution, right? But what you observe here is that it doesn't make much sense to increase too much the number of time slots, even if you are estimating these transition probabilities, because beyond a certain point you are not going to improve. Actually, you are going to have a loss just because of your estimation errors. So it's like, you know, not to exaggerate in allocating power across too many time slots in time, just because we don't know the future, right? So it's better to allocate power only across a few next blocks rather than increasing this number of slots excessively. And again, we can check that there is an advantage, not that big, but there is an advantage in power allocation. So, okay, this is essentially the end of the story. So.
We will have time for a quick question.
Yeah.
So if there is none, I'll have one myself.
Yeah.
Is that when you do some cooperation, you exchange those prices, and then these prices needs to be quantified. So how much do you lose by quantifying those prices in terms of performance?
Quantization.
Yes.
Quantization. Yeah. This is something that we actually did in a recent paper. We did the following. We said, just because we are going to exchange these prices through the backhaul, and that backhaul typically is an internet link, we might have two kinds of problems. One is quantization, the one that you mentioned. The other one is that in some cases there might be an excessive delay in communicating these prices through the internet, which is a best effort communication, right? So we tackled this problem in this way. We said, okay, we assumed a very simple protocol from a network point of view. We said, we establish a maximum delay, and we say that if we receive this price within this delay, it's okay. Otherwise, if the delay is over this value, we just drop. We don't consider that packet anymore. So we consider this kind of random graph again, where the graph describes the links where you exchange these signals, okay? But this graph is random just because on every link, the probability that the link is on is equal to the probability that the packet is received correctly within the maximum delay, okay? So we studied this problem within this random graph theory again, and we proved under what conditions you can still ensure that the system will converge to the right value. So you might still converge. Of course, again, you have to pay something. What you pay is that you need more time. So you don't need to implement a complicated protocol to handle the retransmission of packets. You may drop that. You may be really on a simple case. But you lose in terms of time, because this is what we showed. So, but both quantization errors and random packet drops can be handled in this pricing mechanism.
Okay, thanks Sergio for nice presentation.
Thank you for listening.